Oh, right. Okay. So in the previous part, we have derived the weak form, okay, for the 2D advection diffusion equation. Okay. So this is the basic Galerkin form, right? Okay. So okay, and now we are going to implement this in our code. Okay. In the previous lesson, we have already implemented the 2D diffusion equation, okay, using the 4-noded element. So what we are going to do, we are going to extend that to solve 2D advection diffusion equation. So as you might notice, okay, so the only change we need to do is we need to add the stiffness terms, that is terms to the stiffness matrix coming from the advection part, okay, and there is no change to the force vector, okay. So we need to add this extra term, right? Okay. So first, to help us understand like how the code works and all, okay, so we are going to use the same example that we used for the 2D case, but here I made it into a 2D problem by adding a width of like 0.2 units, and everything else is the same. We know the exact solution, okay, we know how it depends on the Petlet number, okay. So just to recap, so this is what happens as we, okay, as we increase the Petlet number by decrease in the diffusion coefficient. So here, just to recap, okay, so we have the advection velocity in the x direction, that is ax equal to 1. We take as unit velocity, and ay is 0. So there is no advection in y direction. This is the same 1D example. We are just extending it to 2D by making a 2D domain. Okay, so as we decrease the diffusion coefficient, okay, we increase the Petlet number. Okay, so as the Petlet number increases, we see a boundary layer being formed at the right end of the domain. Okay, so the boundary conditions are such that the solution is 0 on both ends, on both these edges. As we increase the Petlet number, okay, so the profile is in from the initial parabolic profile with the pure diffusion. So the profile is going to develop a boundary layer towards the right edge. Okay, so here this is how the exact solution should look like. This is our exact solution. Now we are going to see if we get the solution or not using the Galerkin method. Okay, so like I said, we are simply going to extend the code we have developed for 2D problem. So to start with, I'm going to use this mesh, okay, a 10 by 2 mesh, and then I will refine the mesh. Okay, so what I have done, I have copied the codes from the 2D advection, 2D diffusion that we developed in the previous lesson, and I have renamed them in a separate folder. Okay, so 005 study advection diffusion 2D. Okay, now I am reading this mesh. Okay, advection diffusion example 1 10 by 2 structured mesh, and I need to make some minor changes. So we, since our f is 1, okay, so I have f equal to 1, and for this problem I have created two boundary tags. Okay, so here two boundary tags, left edge tag 1, right edge tag 2, but the boundary condition is the same, that is u equal to 0 on both edges. So what I do, so I extract all the nodes for the boundary lines for the, okay, boundary edge elements. Okay, I flatten the array and then I get the unit nodes on the boundary, like left edge and right edge, and then so these nodes become our degrees of freedom. These are our fixed degrees of freedom, and then we can find the free degrees of freedom. This part is the same, and then we prepare our arrays. So okay, so here since I copied the code, I have this line from the previous example, okay, where we have non-zero display boundary. So what I am going to do, so either I can do this, okay, or I can simply remove this or comment this. Okay, so edit, format, comment. Okay, so we already have the solution array or solution vector where we like initialize it with zeros. Okay, so we don't need to do anything extra, it's unnecessary. Okay, and then everything else is the same. Here the other part is the same, except that we have a new function where we calculate the stiffness and force for the advection diffusion problem in 2D. So again, this function I copied it from the 2D diffusion problem, so I renamed it as 2D like advection diffusion 2D stiffness and force. Okay, I haven't made any changes here yet. Okay, first let us check this example. Okay, for the pure diffusion equation. Okay, so for the pure diffusion equation, we should see a parabolic profile, and we see that, so that's fine. Okay, so next what I'm going to do, I'm going to add an advection velocity. Well, okay, so x direction 1, y direction 0. Okay, and then I'm going to pass it to this function where we calculate the stiffness and force. Okay, so I'm going to add it here. Okay, so now we have access to advection velocity. Okay, so what are the changes we need to make? In the stiffness matrix, we need to add this term corresponding to the advection term. Okay, so that is N transpose AG. So just to help us understand the code better, so I'm going to add some comments. Stiffness matrix. Okay, so here contribution from the diffusion term. Okay, force vector. Okay, in the stiffness matrix we need to add the contribution from the advection term. Okay, so contribution from the advection term. Okay, our determined Jacobian and weight, they remain, we need to keep them. Now the term is N transpose AG. So N transpose A is our advelocity multiplied by G. Okay, so note here our N is 1 by 4 vector. So we need to do N transpose to get 4 by 1, and our advelocity is 1 by 2 vector. So we get 4 by 2, and G is 2 by 4. So we get 4 by 4, which is the size of our stiffness matrix. So if the dimensions of the arrays are not consistent, you need to check and fix them. Okay, so we have added the extra term, the additional term from the advection term. Okay, this is the only change we need to make. Okay, now let us run this. Okay, so there is some error. Line 59. Yeah, so here I'm missing the multiplication. Okay, so that will fit. Okay, so now this is the solution. We don't see much difference here because our diffusion coefficient is still high. See, we have a mu of 1.0 0. Okay. So for yeah, so for mu equal to 1, so this is the solution 0.125. Okay, now what happens if, okay, so this is the solution 0.123. Okay, let's check our solution. Okay, so it's about 0.12. Yeah, so it seems correct. And we can also check the maths value, maths solution. Okay, 0.1226. Okay. Now let's see what happens if we increase the Petlet number, which we achieve by reducing the diffusion coefficient. So we change mu from 1 to 0.1. So as you can see, so the peak has moved towards the right. So here we are noticing the boundary layer being formed to at the left end. Sorry, at the right end. Okay. Now let me reduce it further. Now here what's happening? So now the solution, okay, should be like this. But what we are saying is we are seeing some like oscillations in the solution. Okay, so this is because of the fact that the stiffness matrix is not an M matrix. The same analogy from 1D. Okay, so we are observing the spurious oscillations in the solution. Okay, so we can fix this. We can try to fix this by refining the mesh. Okay, let's see. So I have two more meshes, 20/4 mesh. Okay, so oscillations have reduced, but there are still some oscillations. So that means we need to use a finer mesh. Okay, so I have a 100/10 mesh. Okay, so now the solution looks smoother. Okay, it looks smooth, no oscillations are present here. Okay, and we can clearly see the boundary layer. So the code is working, but because it is dominated by advection, and because the matrix is not a matrix, we have to use a very fine mesh to get an M matrix. Okay, sorry, yeah, because it is a non-self-adjoint system, so we have to use a very fine mesh so that the resulting stiffness matrix is an M matrix. Okay, but this is not what we want to do always. We want to be able to get solutions using coarse meshes because of the computational speed, right? Computational cost. Okay. Okay. So what is the remedy? The remedy is that we add a stabilization term similar to what we did in the case of 1D problem. Okay. So we are going to do that in the next part. Okay. Just to repeat. So for the advection-diffusion equation, the pure Galerkin method, okay, the pure Galerkin method yields results with spurious oscillations if the mesh is not sufficiently fine enough. Okay, we fix it by adding stabilizations